Good morning. Today, this morning we are going to talk about op-amp circuits. In the first half we will cover linear circuits, and in the second half we will cover non-linear circuits. Now Professor Sharma has already introduced the topic yesterday, and some of these things that I am going to show today will overlap with what he has said, but I thought I will just go through these slides so that you can use these in your classroom and in general might find useful. Okay, so let's begin with op-amp circuits. So to begin with, some introduction, and this is always good to tell students so that they know what it's all about, rather than just beginning with the inverting amplifier and so on. So the operational amplifier, the main feature of the op-amp is that it's a versatile building block that can be used for realizing several electronic circuits, and as we will see very simply, and of course you have seen that yesterday already. The use of op-amp frees the user from cumbersome details such as transistor biasing, coupling capacitors, and by this time the students would have already done for example the common emitter amplifier, and they know how difficult it is to design the biasing current and so on. And the temperature changes, the bias currents change and so on, which is a problem. And so the use of op-amp will actually free the user from these cumbersome details and allow the user to use the op-amp almost as a black box. The characteristics of an op-amp are nearly ideal, and therefore op-amp circuits can be expected to perform as per theoretical design in most cases. So the performance or the gain or the frequency etc. of an oscillator will depend in an op-amp circuit will depend only on the external components and not the op-amp itself, as long as the op-amp has high gain. Amplifiers built with op-amps work with DC input voltages as well, and this has to be contrasted with the common emitter amplifier. At this point you should point out to students that if you have a common emitter amplifier and applied small DC voltage like 2 millivolts, even if the op-amp has a gain of 100, it is even if the common emitter amplifier has a gain of 100, it is simply not going to amplify, because the biasing because the coupling capacitor is going to simply block off the DC input voltage. Whereas in op-amps, if you make an amplifier like an inverting amplifier or a non-inverting amplifier, it is going to work with DC input voltages as well as time varying input voltages, and that's a very big plus for op-amp circuits, and it's extremely useful in sensor applications where things are more or less steady, they're not transient. The user can generally carry out circuit design without a thorough knowledge of the intricate details, and we will see what those details are of an op-amp. This makes the design process simple, and you have already seen that yesterday in Professor Sharma's lecture. Okay, so one last point which is very important and which people often ignore, and that is this. Okay, the last point. Okay. And Einstein, of course, was a great scientist, but he also had a great sense of what is required and what is not required. Okay, so Einstein said this: make everything as simple as possible, but not simpler, right? And when you say that op-amp is a black box, when you should realize that it is not a black box, and there are things that we need to worry about at some point. Things like offset voltages, input bias currents. In many applications they are not important, but there are applications where these will play a crucial role, and the user will need to pick an op-amp which has favorable characteristics in that respect. Okay, so we should definitely know where the ideal world ends. That is when you can treat an op-amp as a black box, not worry about it inside, and where the real world begins. Okay, so that's very important, and that is why I am going to show you this figure. That is a block diagram of a real op-amp, and that's 741. Okay, so I'll zoom it to this level, and if you can't see the names etc., don't worry about it. These slides are on the web. You can just download it and view it later at your convenience. But this is just essentially gives you an idea of how complex 741 is inside. 741 is one of the earlier op-amps, one of the first perhaps, and these days we have op-amps even made in CMOS, and they might look quite different than this. So the 741, it has got lots of transistors, some 25, 26 transistors, and this is the input pair. So Q1, Q2 is the input pair, and that is the inverting input. Sorry, that's the non-inverting input. This is the inverting input. And in a block diagram, we show these inverting and non-inverting inputs here. The inverting input and the non-inverting input, inverting input. All right. Then there, of course, there is a supply voltage VCC and minus VEE, and those are shown in op amps like this, VCC and minus VEE. In many figures, we just drop this out because we just assume that they are there. Right. Okay, next. So that is the first stage, and that is the current source, the biasing current source that Professor Sharma was mentioning yesterday. The output of the first stage is taken from here. That's given to the next stage, and then that is an output push-pull pair. Okay, so that's the output terminal. If the current has to be sourced, it is sourced like this. If it has to be sunk, it is sunk like this. All right. Now, I will. The students really at this stage will not know the details, but it is good to tell them that it is complex, and therefore sometimes we need to worry about offset currents, bias currents, slew rate, and so on. Okay. There is this single capacitor here. In this entire circuit, there is just one capacitor, and that is used to compensate the op amp and to make it stable. And you certainly should read more about this in a book like Gray and Meyer or Cedra and Smith. Okay, now because of this capacitor, also there is a slew rate limitation, because this capacitor can be charged or discharged by a certain current coming through this circuit, and that places a limit on the slew on how fast the output can increase or decrease. All right, so all those things are actually not to be explained to the students at this point. We just need to tell them that it is indeed a complex circuit. Okay, so let's go ahead, and this whole complex circuit is represented by this simple block here, and very often we will not even show VCC and minus VEE. Okay, let's go to the next slide. Okay, now as far as this course on basic electronics is concerned, we don't really need to worry about the internal details of an op amp, but just look at it, look at what it does. Okay, so this is the op amp. You will use plus VCC minus VEE like that, and then the equivalent circuit of that entire block is simply an input resistance, which is large. For an ideal op amp, it's infinity. Then followed by current voltage gain, and then there is an output resistance between the output terminal and ground. And very often, or almost always, we say that Ri is so large that this is like an open circuit, and therefore these inputs don't really draw any current. And we say that this Ro is 0, which is realistic in many cases, and therefore this output voltage is simply the voltage gain times the input voltage, and the voltage gain of course is very large. The external resistances, which are of the order of a few kilo ohms, are generally much larger than Ro, this resistance, and much smaller than Ri, this input resistance, and therefore we can assume that Ri is very large, infinity, Ro is very small, 0, without significantly affecting the analysis, and that's indeed what we do always, and that is what makes the op amp such a nice building block. So because you don't need to actually worry about these values of Ri and Ro. Next slide. Okay, next point. Now, since this is the first time the students are even seeing an op amp, it is very important to point out that VCC and minus VEE, which could be plus minus 5 volts to plus minus 15 volts, they must be supplied, otherwise the op amp will not work. And that of course has to do with this previous circuit. Right? If you don't supply this VCC and VE, obviously none of these transistors will get any bias, and things will simply not work. So that's why I'm saying this specifically because there are students in the lab who don't connect these supplies and ask the instructor what is wrong and debug their circuit. It happens very often. Or they don't connect ground. Right? That is also. Ground actually is in the op amp. If you notice, there is no explicit pin for the ground, right? So therefore, all you have is this all you have is this VCC rail here on top and minus VEE rail at the bottom, and therefore there is no connection for 741 for ground, and therefore sometimes people don't connect ground anywhere and then they get into trouble. Okay, and when you do these experiments, the students do the experiments for the first time, they will often make this mistake. That's why it's important to point these out. All right. Next point. Okay, as we have said, in op-amp circuits, the supply voltages are often not shown explicitly, but we understand that they are always there. Now here is a small table which shows the performance of an ideal op-amp and the performance of 741, just some key parameters. So for an ideal op-amp, the voltage gain is infinite. For a 741, it is not infinite but fairly large, 100,000, right, which comes to 100 dB. The input resistance for an ideal op-amp is infinite. For a 741, it is 2 mega ohms. Now 2 mega ohms is still much larger than let's say 1 kilo ohm or 5 kilo ohms, and therefore we often treat this Ri as infinite. RO, ideal op-amp should be 0. For a 741, it is like 50 ohms or 75 ohms, which is still much smaller than these kilo ohms that we normally use in circuits. Therefore we can treat that as 0. Okay, but this table tells you that if you use in an inverting amplifier, if you use 1 mega ohm and 2 mega ohms or 100 ohms and 50 ohms, you will not get the gain that you expect, because then this assumption of Ri being very large, Ro being very small will not hold anymore. Okay, let's go to the next slide. Okay, so the next slide actually is very, very important, and that will also answer the question that was raised yesterday about virtual ground and stuff like that. Okay. So here is the description of an ideal op-amp. We have already ignored Ri and Ro, saying that they're very large and very small respectively. Okay, so if you have that, and if I plot now Vo as a function of Vi, I will get something like this. Now if your saturation voltage or the peak voltage that you can get from this op-amp is, let's say, 10 volts, just as a simple number, 10 volts and minus 10 volts. Okay, then you have a rail to rail a difference of 20 volts and 20 volts and the gain of 10 raised to 5, that will give you something like 0.2 millivolts. Okay, so if you change the input by 0.2 millivolts, let's say you change it from minus 0.1 millivolt to 0.1 millivolt. Remember, we are talking about millivolts here, very small voltage, minus 0.1 millivolt plus 0.1 millivolt. You can change your output from minus 10 volts all the way to plus 10 volts. So it's a very, very small input voltage that gives you a very large change in the output voltage, and that of course is a characteristic feature of the op-amp, a very large gain. If you look at this in a more normal scale, where this goes from minus 5 volts to 5 volts, the output goes from minus 10 volts to plus 10 volts, you see that this entire region, the so-called linear region, gets compressed into just a vertical line. Okay, and this looks more like a comparator characteristics, and an op-amp indeed is a comparator in the open loop, and that's what it boils down to. Okay, so it's very important to show these kinds of figures to the students, so that these things get fixed in their mind, that there is something called saturation, there is something called linear, and the extent of the linear region is very, very small, and small is like 0.2 millivolts, very small compared to any voltages that we normally use, like a few volts. Okay, so what next? So the output voltage Vo is limited to plus minus Vsat, where Vsat is actually depends on that very first block that I showed, and it's about 1.5 volts less than VCC. But in this example, we have taken it as just a nice number, 10 volts, but it could be 12 volts, 13 volts, and so on. Okay, let's go to the next slide. Okay, so let me expand this again. So this is just a reproduction of that earlier figure. So now comes the important point about op-amp circuits. Broadly, op-amp circuits can be divided into two categories, and you must be knowing this already. When the op-amp is operating in the linear region, that's one whole class of circuits. and when the op amp is operating in the saturation region. That's another class of circuits, and these are fairly different in terms of understanding. So therefore, we need to just make a distinction right at the beginning. Okay, now what decides whether the op amp in a given circuit will operate in a linear region, in the linear region or saturation region? That will depend on different things. One, the input voltage magnitude. Two, the type of feedback, and that of course Professor Sharma has pointed out to some extent yesterday, whether the feedback is negative or positive. If it's negative feedback, then the op amp is likely to work in the negative in the linear region. If it's positive feedback, then the op amp is likely to work in the saturation region. And we will take just a qualitative look at feedback a little later. Feedback is very complicated concept, but let's just look at it qualitatively later on. Is the audio all right? Any problems? Okay. So what is the implication of the linear region? Let's look at that now. Okay. So this is very, very important, and it's good to point it out right at the beginning of your op amp lectures. Okay. So we have already said that this linear region is extremely narrow, and if your op amp is in this region, what it means is your V plus minus V minus, this difference here, is the output voltage, which could be anywhere between minus 10 and 10, divided by AV, the voltage gain, and the voltage gain is 10 raised to 5, right, 100,000. What it means is this V plus minus V minus is nearly equal to 0, and therefore we can say that V plus and V minus are nearly equal if the op amp is operating in this linear region. If it is not, if it's in this region or in that region, then of course we cannot say any such thing, and indeed there are circuits in which V plus and V minus can be vastly different. Alright, that's one. So that is simply following from the fact that the op amp is operating in the linear region and that the gain is large. Second, since the input resistance is typically much larger than any other resistance in the circuit, normally this would be in the order of kilo ohms, and the input resistance would be of the order of mega ohms. This input current I in here, that current or that current, is nearly 0. Okay, so that's another very useful feature that we are going to use in analyzing circuits. All right. So all of these linear circuits in which the op amp is operating in the linear region can be understood by these two so-called golden rules. Right. So the one golden rule is that the V plus and V minus are nearly the same. The second rule is that the input bias current of the op amp is 0. These two golden rules enable us to understand several op amp circuits. Okay. Okay, we will not go through this. Maybe let's just go through this linear, the first inverting amplifier, and we will not go through the non-inverting and so on, because Professor Sharma has already talked about this. But here I want to just point out a few things which are included in the slide. You will find it convenient to use in your class. Okay, so essentially it's simply the application of these two golden rules that we talked about. Since V plus and V minus are nearly the same, and V plus is here is 0, therefore V minus is also 0. That's number one. That immediately tells you what this current should be, Vi minus 0 by R1, and that is Vi by R, that is I1. So the non-inverting input is at real ground here, and the inverting input is not at real ground, but it's at virtual ground. It's virtually the same as 0 volts, but not really at 0 volts. Okay, so that's why it's called virtual ground. Okay, the next thing that we use is the second golden rule. Since this current is 0, the current that we calculated must go around like that through this R2, and that immediately gives us the output voltage. Okay, so let's not go to the algebra, it's very straightforward, you have done it yesterday, so this is what you will get. Okay, one important question that students have often asked is what happens to this current? It's an important question to answer, so that nobody has any doubt about that in their minds. Okay, so where does the current go? This is where the current goes. And I need to expand this quite a bit. Alright, so the current that is coming from Vi by R1, that is the current that goes through R2, and then after that, if there is a load resistance, some of that current can go through the load resistance, and some current will always go through the op amp. Even if this, and you know that this circuit works even if there is no load resistance. In that case, all of this current will simply go through this op amp. And now at this point, it is important to connect this simple picture with the actual op amp diagram, and that is just so that people know what is happening inside an op amp, just at least have some idea. So let's do that. Okay, and that is this slide. Right. So if this current is going into the op amp, this is the op amp, then the current actually travels like that. This Q20, which you may or may not be able to read, but I'll just point out the path. If the current is going inside the op amp, then it goes from this output terminal through this transistor into minus VEE. If the current is coming out of the op amp, then it comes from VCC, it comes to this transistor, and then it goes out. Okay. So there's definitely a connection between this detailed diagram and the simple box that you see in the symbol. Okay. So getting back. So let's okay. At this point, it's good to show some pictures so that students get some idea of the usefulness of these circuits. So here there is an input voltage, the red one, and the output voltage, and it's designed for a gain of 10k by 1k, 10 volts. Okay, so that's a picture always helps to fix some things in mind. So you know, students know that this is not in the air; it's actually real. Okay, here is a very important point, something that we actually did say earlier. Okay, now so this is very crucial. Okay, so the gain of this inverting amplifier is minus R2 by R1. Right, it is called the closed loop gain as opposed to the open loop gain, which is very large, 10⁵. The closed loop gain R2 by R1 can be adjusted simply by changing R1 or R2. Okay, it's as simple as that, and you don't need to worry about what this will do to the bias currents inside the op amp and so on. That's very, very important. Imagine trying to do the same thing in a common emitter amplifier. You simply cannot do it. For the common emitter amplifier, on the other hand, the gain is minus GM times RC parallel RL, if you remember all of this. This actually will depend on how the BJT is biased, because this GM depends on IC, and the moment you change the temperature or beta or something, this gain is going to change. And if you change your RL, that will not affect the bias current because of the coupling capacitor, but it will change the gain in a cumbersome manner because it comes in parallel with RC. All right. So the op amp circuits, the design is extremely simple. You just need to design the external components, not worrying about what is inside the black box, the op amp, and that is why op amps are so popular. Okay, now one question that of course will come to students' minds is there a limit to this amplification? And of course there is. If you keep on increasing the input voltage beyond a certain point, the op amp will saturate, and at this point it is good to show a picture like this showing saturation. Okay, so here the op amp is saturated, and therefore it's not useful for this particular input voltage because the output is distorted. Okay, I am not going to go through. Okay, this is another important slide, another limitation that we have in op amp. So not everything is not perfect, and we need to worry about some of these things. If you keep increasing the frequency of the input signal, here it is 25 kilohertz, you will not get the output that you expect. Right? You will expect what you will expect from this red input is the green output. Okay, but that is not what actually happens. What actually happens is this triangle waveform comes at the output, and as you know, this is because of the slew rate limitation of the op amp. The slew rate limitation is basically that the output can only change or increase or decrease at a maximum rate. For 741, it is 0.5 volts per microsecond. Let me check that. So the slew rate So this is a slide that you can show to explain what slew rate does to an inverting amplifier. The slew rate of an op amp is the maximum rate at which the op amp output can rise or fall. For the 741, the slew rate is 0.5 volts per microsecond, and in fact you can see these slopes. These will turn out to be more or less that 0.5 volts per microsecond. And if why is the output not given by this green curve, which is the theoretically expected output? Because the rise here is faster than what the op amp can give you. The op amp can only give you this rise, and this rise here actually is far higher than 0.5 volts per microsecond. Therefore, the op amp cannot keep up with the input voltage. What do you do in such cases? In such cases, you choose an op amp which has a higher slew rate, and there are, of course, these op amps will be more expensive, but they are available in the market. Don't ask me what the number is, but you can look up the web and you will find those. Okay, so let's go ahead and I'm not going to talk about. Okay, I'm not going to talk about non-inverting amplifier, but before we leave the topic of inverting amplifier, here is one very, very important point, and it is something that a doubt that lingers in students' questions, and it must be clarified. All right, now if you look at our analysis, how did we analyze this circuit? Okay, we said that these two are virtually the same, so therefore this is 0 volts. Then we calculated this current. We said that this current also goes like this, and then we said that VO is 0 volts minus I1 minus I times R2, and therefore we got minus R2 by R1. Now suppose this plus and minus were actually exchanged. Okay, you will get this circuit, and if I carry out the same analysis once again, I will again get the same expression. Okay, and reality, of course, we know that this will not happen. This circuit will not act as an inverting amplifier with this as plus and this as minus, and that is very, very difficult at this stage to explain. So we can just, as far as the students are concerned, we can just refer to feedback at this point and just leave it at that and tell them that if this circuit will not actually work, and we'll come back to that later. Okay, so why does it not work? Because our assumption that the op amp is working in the linear region does not hold in this circuit, and that's because the feedback has become positive. Now it turns out that the circuit 2 is also useful, which is actually a Schmitt trigger, and we will discuss that later. Okay, so that's one important point you must make when you are before leaving the topic of the inverting amplifier. So even about even when we talk about the inverting amplifier, there are so many things that textbooks don't talk about. Textbooks will only show the circuit. They will say, okay, VO is minus R2 by R1. There is a negative sign, therefore it's called inverting amplifier, and they will stop at that. But there is so much that I mean, there's so much more to it. For example, the op amp saturates if the input voltage becomes large. The op amp is slew rate limited if the input frequency is high, and so on. All of these things are very often not even mentioned in textbooks, and that gives the wrong, very often gives the wrong impression to students. So it's important to just point these out, and all of this can be done if you just show a simple, show a few pictures, even without a detailed explanation. Right. So now let's go to. We will not go to the non-inverting amplifier because it's fairly straightforward. We have done it yesterday as well. Okay, this is an important question. Inverting or non-inverting? Which one will you choose? Okay, let's say we want the gain of 10. I can make R2 by R1 10 here. I can make R2 by R1 equal to 9, and I'll get the same gain in both these circuits. Which one of these is preferable? Okay. Of course, one thing is the sign here is different, but let's say we are not bothered about the sign. We are just bothered about the amplification. Then which configuration should be preferred? So that's an important question, and the answer has to do with the input resistance. The input resistance in this circuit is R1 because this is at virtual ground. Input resistance in this circuit is the input resistance of the op amp, which is very large. Therefore, the non-inverting configuration is preferable if your input resistance is a constraint in your circuit. Okay, so the rest of the slide just says these points. So let's go ahead. All right, what is a special case of the non-inverting amplifier? Is the buffer. And what is the buffer? With R1 very large, that means open circuit. So you have an open circuit here, and R2 very small or 0 ohms. You have a short circuit here, and that's called a buffer. And so the gain of this circuit becomes simply 1. So VO is equal to VI, and of course it looks, at the first glance it looks like we have not achieved anything, because we just reproduced this VI without really amplifying it, and students will wonder at this stage what is the use of this. And then we need to talk about how an amplifier, or how a load will load an amplifier, and how a buffer helps in solving that problem. Okay, so let me okay, let's just illustrate that point. Suppose you have an amplifier like this, right? So there is an amplifier with a source voltage Vs and an output resistance RL. Now from this amplifier, its gain is AV, and you would expect the output voltage to be AV times Vs, right? And that is in the ideal case. In practice, what happens is, because of this RS and RI, because the RI is not infinite, there is a voltage division here. Because this RO is not 0, there is a voltage division here, and then you will end up with, instead of AV times VI, you end up with AV times this voltage division factor times this voltage division factor times Vs. Okay, so that is not desirable, and that is where a buffer can help. Okay, so there is one more slide which explains that, and you can go through it later. But that's an important point to explain when you talk about a buffer. Okay, so I'll skip that. Here is an example where a buffer is useful. Okay, op-amp circuits linear region continued, and this summer is simply an extension of the inverting amplifier, and it is a good circuit to describe at this stage. Okay. Can we make this full screen or something? Is it possible? Otherwise, every time I go to the next slide, this is it possible? No. Okay, so let's look at the summer. Again, it's a circuit in which the op-amp is working in the linear region, and therefore this V minus is virtually the same as V plus, which is 0, and so on. Then you can calculate all of these currents, I1 and I2 and I3. Then the second golden rule, that the input current of the op-amp is 0, therefore all of this current, which is I1 plus I2 plus I3, will go through RF, and eventually you can calculate the output voltage. Okay, you know all that, and that is what you will get. And let's not go through it. Okay, but I wanted to show you this figure, which can be useful for students to understand what's going on. Okay, so in this figure, we have 3 input voltages. Vi1 is a DC voltage of 1 volt. Vi2 is this green one. Vi3 is the yellow one. And this circuit is going to add all of them. I think R1, R2, R3 are all equal to 1K, and RF is 2K. So you are going to get VO is equal to minus 2 times all of these voltages added, and that is what your output comes to. And you see that this DC voltage 1 volt has given you a shift of minus 2 volts at the output, and it's also a good way to point out that the op amps work for DC input voltages as well as AC input voltages, which a common emitter amplifier cannot do. So it's just goes to show that the versatile nature of the op amp as a building block. So there is one question: why external resistance is larger than RO and smaller than RI? Okay, it is by design. When you make an op amp circuits, you use resistors like 1K, 5K, 10K, 50K, but you don't use things like 1 meg or 2 meg or 10 meg, or you don't use things like 5 ohms, 10 ohms, 50 ohms, right? So it is by design. It is not, and it is because the op amps have finite RI and RO. So what will be the output of an op amp with AC input of 50 millivolts on one terminal and 50 millivolts DC on another terminal. Okay. If you are using the op amp in the open loop, 50 millivolts DC and DC on one terminal and 50 millivolts AC on the other terminal. Okay. So the op amp is in the open loop. Op amp is going to act like a comparator, and you're just going to get a square wave, maybe with whatever duty cycle decided by these numbers. That will also, and if you are using the op amp in the open loop, you need to actually worry about the offset voltage. So the output will also depend on what is the output, the offset voltage of the op amp, not just your inputs, especially if the inputs are so small. How to check the status of an op amp IC in a lab? The status of an op amp? You mean, the question is not very clear. I can see that this question can mean two different things. One, whether the op amp is working. To check that, there is something called a linear IC tester. You can just plug the IC into that machine, and then it will tell you whether it works or not. The other thing is to hook up a simple inverting amplifier and see if it works. But how to check the status of an op amp IC in a lab? If you have a working circuit and you want to know whether it's in the linear region or not, just look at V plus and V minus. If they are very close, then it's in the linear region. Under what circumstance op amp amplifier alternately coupled is used? I don't quite understand this question. As far as op amp amplifiers are considered, like inverting, non-inverting, you can connect AC inputs directly to the inputs. You don't really need any coupling capacitors. Okay. All right. So let's go to the next part of this. 10:30. Op amp circuits part 2. Okay. So I think in this part we are going to continue with linear circuits as well. Let's go to the next slide. Okay, one very important concept that students are often not very familiar with is the so-called common mode and differential mode voltages and the common mode rejection ratio. It's so important that it has to be really drilled in with some example at an early stage. Okay, so let's just take this example, and this is a very, very typical instrumentation amplifier kind of application. Let's say you are sensing a temperature or pressure, and that sensor, that quantity is going to influence one of these resistances. For example, if it's a strain gauge, then this resistance is going to be mounted on the strain, on the part that you're going to measure the strain of, and all these others are constant. Okay, so this is a very very commonly used bridge configuration. So let's look at this common mode and differential mode voltages in the context of this common application. Okay, next. So let's consider this bridge circuit for sensing temperature, pressure, etc. with RA, RB, RC all equal to R, and this RD we will say varies with the quantity to be measured. It could be temperature, pressure, strain, etc. So this all of these RA, RB, RC are equal to R, and RD is equal to R plus delta R, where delta R could be positive or negative depending on whether the temperature or pressure is more or less than the nominal temperature. Okay, next. So the bridge, what is the purpose of this bridge? The bridge converts this delta R, which is a result of a temperature change or a pressure change, to a signal voltage. And where is the signal voltage taken? That is taken between V1 and V2 here. And of course this voltage is going to be small because delta R is small, and then therefore that needs to be suitably amplified, and that is the purpose of an amplifier. And this could be a difference amplifier, it could be an instrumentation amplifier, and then we will see why an instrumentation amplifier is used. So let's look at this particular bridge circuit, and this essentially is the motivation for a large common mode rejection ratio and definitions for this common mode voltages, differential mode voltages and so on. So assuming that this amplifier has a large input resistance, what it means is this current and this current drawn by the amplifier is 0. In that case, V1 is going to be simply RB by RA plus RB times VCC, and that is just half VCC. So V2 is RD, which is R plus delta R, divided by RC, which is R plus RD, which is R plus delta R, times VCC. So if I put X, a small number, the fraction as delta R by R, then I get half 1 plus X by 1 plus X by 2 times VCC. And X is a small number, it could be like 0.05, 0.02, 0.1 plus or minus, depending on the quantity that you are measuring. And I can use this, I can simplify this using approximations, and I get finally something like this, half 1 plus X by 2 times VCC. So this V1 here is half VCC, V2 here is half VCC plus a little bit extra, okay, and that extra quantity is actually proportional to the signal that you are trying to measure. And it's good to take an example at this point, just to fix these ideas in the mind of the student. So let's take an example. Let's say VCC is 15 volts, R is 1K, delta R is a small number, 0.01K. So this is like 1% of the nominal value, and V1 will be VCC by 2, which is 15 volts by 2, 7.5. V2 will be 7.5 plus that X by 2 factor, and that comes to 0.0375 or 37.5 millivolts. So the differential mode signal that you are looking at, the difference between these two is actually very, very small compared to the common mode, which is large, 7.5, and that is actually the key to instrumentation amplifier. Okay, so next slide. So this is the same circuit as before, and let me and this is what we got earlier. So the V1 node was sitting at 7.5 volts, V2 is sitting at 7.5 plus a very small number, 37.5 millivolts, much smaller than 7.5 volts. And what we would like to do is to amplify only V2 minus V1, that we would actually like to amplify only this 0.0375, okay, and not this 7.5, because that is the quantity that is proportional to the signal that we are trying to measure. So, and now at this point we need to define a few things. What is the common mode voltage defined as? It's half V1 plus V2. In this case, V1 and V2 are nearly 7.5 volts, and if you take half of that, you will just get 7.5 approximately. VD is the differential mode voltage, and that's the difference between V2 and V1. In this case, that is 0.0375, okay, or 37.5 millivolts. So these are the definitions. So the common mode voltage is defined as V1 plus V2 by 2, the average of the two. Differential mode voltage is defined as the difference between the two. And in this case, as we said before, we would like to amplify only the differential mode part and not the common mode part. So what is the important point to note in this particular slide? That is here. Note that the common mode voltage is quite large compared to the differential mode voltage. It's 7.5 volts compared to the 37.5 millivolts that we are trying to measure. And this is a very common situation in transducer circuits, because we are always going to use some bridge, and therefore this is very common. Okay, now this leads us to the definition of the common mode rejection ratio. Okay, so here it is once again, and there is an amplifier, V plus and V minus. So V plus, V minus are the inputs to this amplifier, and it has got a common mode component Vc and a differential mode component Vd. So V plus is Vc plus Vd minus Vd by 2, V minus is Vc minus Vd by 2. So an ideal amplifier would only amplify the difference between these two, and that is just Vd, and that will give you some gain times V plus minus V minus times Ad times Vd, where Vd is called the differential gain or simply the gain, Av. In practice, as we know, the amplifier will also amplify the common mode component, and the actual output will be given by the Ad times Vd, which we want, plus some common mode gain times Vc, which we don't want. Okay, so AC times Vc is the output voltage that we actually don't want. In fact, we want it to be 0, where AC is called the common mode gain. So this is now very important. The ability of an amplifier to reject the common mode signal is given by the common mode rejection ratio, CMRR, and that is simply Ad by AC. So if AC is small, Ad is large, then CMRR is going to be large, and you want this CMRR to be infinite, or as large as possible. For the 741 op-amp, the CMRR is about 90 dB, which comes to 30,000, and 30,000 in many cases is considered large enough, and we might in fact say that it is infinite. Okay. All right. So now, even if the op-amp has an infinite common mode rejection ratio, there are still some problems. There are still some mismatch issues between in the resistors that you use. For example, let's take an example in the next slide. Okay, we'll come back to the CMRR later. Okay, so let's look at two circuits. One is the difference amplifier, the other one is the instrumentation amplifier, and see how they perform with respect to these kinds of applications where there is a large common mode voltage and a small differential mode voltage. So this circuit we have done yesterday. I will not do it. I will not go through the derivation, but I would like to point out here that this the gain of this circuit can be derived in two ways. One, the usual way, just assume that just use this fact that I plus is 0, calculate this V plus equal to Vi2 times R4 by R3 plus R4, and V plus V minus being the same, this voltage is also given by the same expression. Then you can calculate this current, and you know this current goes like that, and then finally you get the output voltage. So this is something that we that is standard, and we that's certainly one way of doing it. The other method of deriving this result, the same result, what is the final result? Let me just read it out here. R2 by R1 okay. So the result is VO equal to R2 by R1 times Vi2 minus Vi1, and you have done, Professor Sharma has done this yesterday, but I just wanted to point out another interesting way of deriving this same result, and that is by using superposition. Okay, so let me explain that. Okay, now this circuit actually, since the op-amp is in the linear region, we are free to use superposition. And what does it mean? It means I can make this Vi2 equal to 0, apply Vi1, calculate Vo1. Then I can make Vi1 equal to 0, apply Vi2 and calculate Vo2. And finally my output Vo is given by Vo1 plus Vo2. So that is another way of doing this, and you can look at this details later. Just gives the student some confidence that superposition and all these things actually work in practice and are useful. Okay, let's go to the next slide. So this is something that Professor Sharma was anyway doing yesterday, R2 by R1 times Vi2 minus Vi1. Alright, now let's get back to, okay, let's put together our sensing mechanism, this bridge circuit and the difference amplifier, and see what happens. Okay. So we see some problems. If I do that, so there is this V2 minus V1 that this circuit is going to amplify, and we see that since this circuit only amplifies V2 minus V1, that is exactly what we want. That is right now is not a problem, but there is a problem because of the loading of this circuit of the bridge. Okay. So what happens is if I just connect these two directly to these two terminals, the inputs of the op-amp, inputs of the difference amplifier, then this from here we are going to see some resistance R3 plus R4, and that is going to come in parallel with RD, and therefore I am going to basically disturb this value of V2, which I expected to be something. It's now going to be something else. So there is a problem there. Okay, and that is because this difference amplifier does not have a large input resistance. So that is one problem. We will also mention another problem. So the resistance seen from V2 is R3 plus R4, which is small enough to cause V2 to change, and that of course is not desirable, because then we are not going to measure what we intend to, because it's going to be modified by this R3 plus R4 factor, and that's something that we certainly don't want in a good instrument. So they definitely need to improve on the input resistance of this difference amplifier. Okay. So we will discuss and improve difference amplifier later, but before we do that, let us point out another problem. Let us discuss another problem with the about difference amplifier, which can be important in some applications. So let's look at the next slide. So in the next slide, we are showing this difference amplifier again. Okay, and we are applying Vi1 equal to Vc minus Vd by 2 and Vi2 equal to Vc plus Vd by 2, where these are the common mode voltages and the common mode and differential mode voltages respectively. Alright, now let's say the op amp is ideal and it has infinite common mode rejection ratio. So the CMRR of the op amp itself is not an issue, but even these R1 and R2 would not be exactly matched. For example, this R3 is expected to be exactly equal to R1, R4 is expected to be exactly equal to R2. In reality, they are going to be slightly different because these resistors have some tolerances and they are not going to be exactly equal. So let's just take an example and say that R3 is not exactly equal to R1, but it is R1 plus some delta R. Okay. In that case, what you get is this expression. You can show this. And then you will get R2 by R1 times Vd minus x times Vc, okay, where x is delta R by R1 plus R2. Okay, show this. This is very important. Don't just take my word for it. Go through the algebra, do the simplification, and show that you actually get this result. Okay. So what is the bottom line? The bottom line is that now we have a Vc here, the common mode voltage, which was not there earlier in our expression. Earlier we had just R2 by R1, Vi2 minus Vi1, that was fine. Here now we have R2 by R1, the differential mode input, and there is a common mode term. Okay, and of course the common mode term is going to get multiplied by a small number x, but let us see, it might still have an effect. Okay, now, so what is the key? The key is that this Vc is much larger than Vd, and therefore even if this x is small, this term and this term actually could be comparable, and that is a problem. And then so what you would think is a purely differential mode output will be sort of corrupted by this common mode term, and we don't want that. Okay, so let's just take a look at some numbers. Okay, let's just look at this specific example. The same example as we had before. In that, the common mode voltage was 7.5 volts, Vd was 0.0375 volts, and now what is the common mode term in the output voltage? That's x times R2 by R1 times Vc, and that is 0.75 volts. What is the differential mode term in the output voltage? That is R2 by R1 times the differential mode voltage, and that is 0.375 volts, right? So in fact, the common mode voltage is a completely spurious output that we don't want, but it is substantial. You can see that in fact in this particular example, it's even larger than the differential mode contribution to the output voltage, and therefore if you measure measure the output voltage, you are going to get you're going to get a wrong value of the output, and therefore this is not desirable. So therefore we need a circuit which will reduce the common mode component at the output. So in summary, what we had, we discussed two problems with this difference amplifier. If you are going to hook up a bridge circuit here, then it's going to change the voltages in this bridge circuit. That is one, because its input resistance is not very large. Second, if there is a component mismatch between, let's say, R3 and R1, or even R4 and R2, we took just one example, then it is going to lead to substantial common mode voltage at the output, which is going to spoil over the operation of the circuit. Okay, so how do you improve this? And that answer you should already know, and that is the instrumentation amplifier. Okay, so here is the instrumentation amplifier. So at the outset we notice that it is not just one op amp but 3 op amps, so it's definitely going to be more expensive than a simple difference amplifier, but it of course comes with its advantages, and that's why it is used. Okay, so first thing that we notice is this Vi1 and Vi2 are now going to see the input resistance of the op amp, which is of the order of mega ohms, right? So you're going to see some mega ohms here, you're going to see some mega ohms here. and therefore if I connect this to a bridge circuit, that is fine, because then that bridge circuit operation is not going to be disturbed. So that's one very important point. The other important point has to do with the common mode rejection ratio. Okay, all right. So and that is what is explained in this particular slide. So let's see what that says. Okay, so how does this circuit work? It's very simple. V plus is nearly equal to V minus, for if the op amps are operating in the linear region, which they are in this circuit. Therefore, this VA, this voltage here, is the same as VI1, and VB, this voltage here, is the same as VI2. Okay, so we have VI1 here and VI2 here. All right. So what is this current I1? This current I1 is simply VI1 minus VI2 divided by R1. Okay, that is what this shows here. Now, since no current can go into the op amp, either here or here, what we can say is that this I1 is also the same current in these resistors R2 and this R2 and this R2, right? So that entire this I1, the path that it will follow is like this, right? And therefore, this VO1 minus VO2 is going to be R2 plus R1 plus R2 times I1. And that is, and finally what you get here is simply the same difference amplifier that we have seen before. Okay, and if you put all of these things together, then you will get this expression: R4 by R3 1 plus 2 R2 by R1 times VI2 minus VI1. Okay. Now, how is this an improved circuit in terms of the CMRR? And the reason is very simple. Okay, let's consider that this VI1, maybe I have another slide on that, let me just see. Yeah, so this is simply an illustration of what we were just saying. Even if I hook up another circuit here like the bridge, this is going to draw very small current, zero current, and therefore this V1 is not going to change. This terminal is also going to draw a very small current, therefore this V2 is not going to change. So in other words, by hooking up this instrumentation amplifier to my bridge circuit, I am not going to disturb the measurement. Okay, that is important, and that is because of these large input resistances of these op amps. Okay, next, so the next slide talks about the CMRR. Let's look at that. Okay, why is this a better circuit as far as CMRR is concerned? That is given here. So as we have seen earlier, VI1 and VI2 can have a large common mode component Vc. All right. So as we have seen earlier, VI1 and VI2 can have a large common mode component, and we saw an example where this Vc was 7.5 volts, very large indeed. So what is the effect of Vc on this particular instrumentation amplifier circuit? Let us see. Okay. So at this node Va is Vi1, and let's say that is going to be given by Vc minus Vd by 2. Okay, the common mode component and the differential mode component. Vb, as we said, is the same as Vi2, and that is the common mode component Vc plus Vd by 2. Now, will this current change because of the common mode voltage? Actually, turns out it does not change, because this current will still remain Va minus Vb divided by R1, and that is this term minus that term. And you can see that this Vc is simply getting cancelled, and you are getting this current dependent only on Vd, which is a very nice thing. Okay, and this holds even if your R2 and R2 prime are not matched. Right? Normally they are supposed to be the same, but even if R2 and R2 prime are not exactly equal, suppose this R2 prime is equal to R2 plus delta R, this current will still not have any term in Vc. Okay, and that is why the output of this circuit will not depend on Vc, the common mode input voltage. Very important feature of the instrumentation amplifier. Okay, so the instrumentation amplifier improves on the difference amplifier in two aspects. First, it provides a large input resistance at both these terminals, and it provides an excellent CMRR. In fact, in this ideal case, the CMRR is infinite, because there is no output, there is no Vc at all in this output voltage. Okay. Then there are a few other things. Let's just talk about current to voltage conversion. Actually, I think I have more material than I have time for, so I'll have to at some point choose between topics. But let's look at this current to voltage conversion. Why are we worried about current to voltage conversion? Because some circuits produce an output in the form of a current. Okay. For example, if you shine light on a photodiode, the output is in the form of a current, which we would like to convert into a voltage. So if the output of a circuit is a current, it is convenient to convert that into a voltage for further processing, and that is why we need a current to voltage conversion. Okay, what is the simplest current to voltage conversion you can think about? And that is a simple resistor, and so you pass the current through a resistor, you will get VO equal to IS times R. Okay, so that is the first thing that comes to mind. Not adequate, of course, because of loading effects. Suppose you have this simple resistor to convert your current into a voltage. Now if you don't have anything connected to it, VO1 is IS times R. Now the moment you have an amplifier connected to this circuit, it is not IS times R anymore, because this R is now going to be R parallel Ri. So it is going to be VO1 equal to IS times R in parallel with Ri, and that's so your input voltage itself is going to change, and therefore what you measure will depend on the input resistance of the amplifier. Therefore it's not desirable to have just a simple resistor to convert a current into a voltage, and that is where op amp again comes to your rescue, and let us see how. Okay, let's go to the next slide. Okay, so again the operation of the circuit is extremely simple, and it is like this. So there is a current, and we know that this current entering the op amp is 0, therefore this current has to go like this, and of course eventually it will go into the op amp and so on. Not a concern right now. So and this, since the op amp is in the linear region, we say that P minus is nearly equal to 0 volts, and the output voltage then is 0 minus this current IS times R, and that's exactly minus IS times R. So you have an output which is proportional to the input current and just a multiplying factor R. Now note that here, although we have a load resistance here, it does not enter this expression, right? So there is no dependence of the output voltage on the load resistance, and that is an extremely desirable feature of a current to voltage converter. That will not happen if you just use a simple resistor to convert a current into a voltage. Here is an example, a reverse biased photodiode. You shine light on it, it generates a current, and that current will produce an output voltage. So these things are used all over the place for sensing light. Okay, so that's okay. Let's go to the next integrator. I think Professor Sharma has already talked about this yesterday. We will not discuss this further, but I just wanted to point out that there are some plots that you might find useful. Okay, so here is a plot. If there is an input voltage of this kind, that is the output voltage, and you can actually show this in the class if you like, and ask the students that to verify that this output voltage is going to be a certain value and so on. Here is a square wave example and our corresponding output voltage for certain values of R and C. Okay. Then there are non-idealities in op amps like offset voltage, bias currents and so on, and I put all this material in the slides, but in a basic electronics course probably there is not enough time to cover these things, so I will not really talk about this right now, but you are welcome to just look at it later. This table may be interesting to you, okay, and if somebody actually is building an application which requires the bias current to be very small, then appropriate op amps can be picked. For example, the 741 has got a bias current of 80 nanoamperes, an offset current of 20 nanoamperes, that means the difference between this current and that current, and an offset voltage of 1 millivolt. Okay. Now, suppose you have an application where you are not satisfied with 1 millivolt, then you can go for a more expensive op amp and higher performance. So this OP77 has got 10 microvolts offset voltage, okay, 1.2 nanoamperes bias current, 0.3 nanoamperes offset current. So these two have BJT inputs, and if you want a really low input bias current, you can go for a FET input op amp, and it's a 411 that has got a bias current of just 50 picoamperes, and that of course has to do with our JFET lecture yesterday. The JFET has got a reverse bias PN junction at the gate, and therefore the currents are very small. So it's good to at least give some idea to the students that op amps with various specs are available in the market. Okay, so there are some other slides that we can skip. Okay, I just have a few slides on filters, and Professor Sharma has already talked about filters yesterday. But I thought I'll just share with you some of the slides which you might find useful to show in class to explain what a filter is all about. Okay, in this slide we have two voltages, V1 a low frequency voltage and V2 a high frequency voltage, and we are going to add these two, V1 and V2. Right. So this essentially is the motivation behind filters. What is the motivation? Why do you need filters? So this slide can be used for that purpose. So in practice what we have is we have a signal like this, which is a sum of two signals, and we want to see either the low frequency part or the high frequency part, and that brings us to a low frequency filter, a low pass filter, which will give you, if I apply this if I pass this through an appropriate low pass filter, I will get this V1 as the output. If I apply this, if I pass this through a high pass frequency high pass filter, I'll get V2. Right. So it will pass V2 and block V1. So that is just a motivation of V1 of filters. What filters are all about. Okay. And before we actually go to op amp filters, it is good to explain what ideal filters look like. Okay. So an ideal filter actually looks like a gain of 1, that is pass, and a very sharp fall with infinitely fast fall, and then 0. That is what an ideal low pass filter would look like. And here is an illustration of what it does. Okay. So this is the Fourier transform of an input signal. It has got a component, two components before omega c, where omega c is the cutoff frequency of this low pass filter, and two components at which are higher than omega c. Okay. Now you are making this go through this particular filter, and what this will do is it will chop off these two components, and it will keep these two components, the lower ones, and that is the, if you look at the spectrum after at VO of t, then it will look like this. So it's good to explain filter operation in this manner. Okay, what are the various kinds of filters? The low pass, band pass, and at this stage it is good to still consider ideal filters with sharp edges, okay, and then come to real cases. Okay, so here is an example. Again, this is something you will find useful in illustrating what is a low pass filter, what is a high pass filter, what is a band pass filter, what is a band reject filter, and so on. Okay, so let's go back, let's just look at this slide in more detail. Okay. Now you may not be able to view this too well, but go back, look at these slides later on, download these and see. So the first example shows a filter which is a low pass filter, one up to here, sorry, I need the pointer. Okay, one up to here, and then a sharp drop, and then 0 here. Okay. Now if I apply this signal, that is a combination of V1, V2, V3, I get this. If I apply this signal to this particular filter, what it will do is it will remove this particular component, that is this pink component, and it will pass the other two. It will remove these two components, that will pass the ping component, and that is what you get. So just go through this slide, and things are of course self-explanatory, and you can understand what is happening in each case. Okay, what are practical filter circuits? In practical filter circuits, the ideal filter response is approximated with a suitable h of omega, h of j omega, which that can be obtained with circuit elements. For example, h of s could look like this to represent a fifth order low pass filter. And in the rest of this PDF file, we have only examples. Here we show an ideal low pass filter and an actual low pass filter. Okay, and then there are these definitions that there is this pass band and stop band and so on, and some filters will have these oscillations, and then of course the sharp is not extremely sharp, but there is some dB per decade fall and so on. So that is this is an ideal case, and that is a practical case, and the student should actually know about this. Similarly for high pass. All right, I'll just show some examples, and then I think we will end the lecture. And these examples you can actually show in class, because then filters is something which is very difficult, because it's not possible normally to plot all of these things on the board. So if you have some ready-made material like this, it might be useful to you. So here are Butterworth filters, order 1, order 2, order 3, order 4, order 5, and that is what H looks like on a linear scale. Okay, now when we talk about filters, the linear scale is not very useful, because then we can't make out the order of the filter very well. So therefore, we can plot H in dB and omega in log scale, and then this thing comes out very clearly. So n equal to 1 filter will have a slope, will have a drop of 20 dB per decade. This will have 40 dB per decade, and so on. 5 will have 100 dB per decade. Okay, so and these are the Chebyshev filters, and you can point out the difference between Butterworth and Chebyshev. In Chebyshev filters, you have these little wiggles in the pass band. In Chebyshev, this is flat. Okay, in Butterworth it is flat. Apart from that, of course, this for the same order n equal to 1, the slope here will be 20 dB per decade. The slope here also will be 20 dB per decade, and so on. So just wanted to share with you some of these figures which may be useful to you. High pass, and then there are some examples. Okay, let me just show some examples. And all of these examples are actually ready-made examples in the SQL distribution. So you can even ask the students to vary some parameter and see what happens, and so on. That can be useful to them. So here is a low pass filter, and for this simple cases like this, you can actually derive these results in class, and then show this figure that this is what it will do. High pass filter, and then there are some more complex examples. Second order, it's a band pass filter. Okay, this is a graphic equalizer. We don't have time to go through this, but it's a circuit which is not given in standard textbooks, but it is useful to in the real world. And students might particularly get quite excited about this, because this has to do with audio amp applications. So it's good to show them that some of these things actually are useful, used in day-to-day life, and are directly applicable. Okay, so there are more figures, and we will stop at this point. Maybe I can just take a few questions.